Okay, we're going to look at the principal moments now. We're going to look at more difficult examples and we're going to apply them. So first of all, the principle of moments is where we've got, the principle of moments is to do with ideas that when something's in equilibrium, the net moment is zero. We can use that idea a little bit more specifically to do with moments, and we can say that the sum of the clockwise moments is equal to the sum of anti-clockwise moments. So the principle of moments is the idea behind the sum of the clockwise moments is equal to the sum of the anti-clockwise moments when it's in equilibrium, when an object's in equilibrium. So we're going to look at a standard example here, which is a seesaw. Two people on our seesaw. We've got one that's 3 meters away, one that's 2 meters, and obviously they're going to have a force. So I'm going to say that's, let's go with 700 newtons, that sounds good. So 700 newtons, and we have an unknown. So we can use the principle of moments here to work out our missing value. The sum of the clockwise moments, well, let's look at these moments carefully. We've got a situation where we've got two directions. We've got this one here. That one is going anti-clockwise. This one, clockwise. So what we're going to say is that our force times our distance for our anti-clockwise moments is going to equal the force times the distance for our clockwise moments. So that means that we can say that 700 times by 3 is going to be equal to some unknown times by the distance, which in this case is 2 meters. And so what we're looking at here is we're looking at doing a simple rearrangement to get us to the final answer. We're going to be looking at doing 700 times by 3 divided by 2, and that will give us our unknown force there, which 2,100, 1,050, so 1,050. So 1,000 newtons. So that means that the force or the weight of this person is 1,050 newtons. And that pretty much is the most simple form of this. Now bear in mind, if you've got more than one force on a beam or a seesaw or anything like that, then you're going to have to add that into the anti-clockwise or clockwise, but we'll do some examples and maybe you can find one or two where you've got more than one clockwise and anti-clockwise moment, but it's still in equilibrium. Remember, if it's still in equilibrium, this has to apply, okay? Right, before we go, let's have a look at a more difficult example to set you up for class. So, we've got two supports that are holding up a beam. Box on. Now the box weighs about 200 newtons and the beam itself weighs about I'll say another 200 newtons, make it nice and simple. So we've got 200 newtons and 200 newtons, and we're going to call this beam A and we're going to call this beam B. And the idea of this is to work out what the force upwards at A and B is, given we've got some distances. Lovely. Okay, so we're saying that the beam is about 20 metres long. To the centre of gravity of the beam, 10 metres. To the box, 7.5. So, where do we start with a question like this? Because quite simply, I've got two unknowns. If I need to work out the force upwards at A and the force upwards at B, I'm going to have to do what I like to call assigning a pivot. So we can assign a pivot here. We're just going to pretend we don't really care about this force for a second. We do care, but we don't really care about it for a second. We're going to call this the pivot. It's a nice idea when you see questions like this, that if you get a given distances from a position, it's a good idea to suggest that that is the pivot. Okay? So you've got a number of different moments that are going on here around this pivot. So let's do some working to work out what one of my unknowns is. So this is the first unknown I'm going to work out. So I've got a clockwise, two clockwise, and one anti-clockwise. So these two are clockwise moments, and this one's an anti-clockwise about this pivot. So let's have a look, and we look at these individually, we add them all up. So remember, sum of the clockwise, so we've got 200 times 7.5 plus 200 times 10. That's the sum of my clockwise moments, and that's going to be equal to 20 times by my unknown. So we can do a bit of algebra here just to simplify this straight away. 200 times 7.5 plus 200 times 10. Divide that all by 20 and we'll get an answer. So let's do that on our calculators now. So 200 times 7.5 plus 175. So your answer should be 175 newtons. And that's telling you that there's 175 newtons acting upwards at this point here. So we've done one of the two unknowns. Happy days. What about this one then? Well, we could think about this and a different way round and say, oh, well, now I've got to make this the pivot and work out new distances for everything. You can do that. Feel free to have a go at it. Or you can work it out the quick way. Remember what I told you in the previous video about equilibrium. This is an equilibrium. The first rule was net forces equal 0. The second rule was net moments equal 0. Now we've used the net moment idea here to help us work out what an unknown is. Can we use the first rule? Well, if you look carefully here, net force has to equal 0. I've got 400 newtons down. And I have 175 newtons up. Great if you've already guessed it. I can work out real quick what A should be based on the first requirement for equilibrium, which is net force equaling 0. We've got 175 up, 400 down, there's an imbalance there. This must make up the difference, so we should have a difference of 225 newtons here. And that should add up nicely. So if we've got 225 plus 175 equals 400, lovely. 200 plus 200, 400. So I've worked out my unknown based on the principle of moments and using the idea that for equilibrium to be the case, that we have net force equals 0 as well. So both of these different ideas need to be employed when dealing with moment and equilibrium problems. And have a go at a couple before you come to class, so we can deal with any issues you might have. Okay.